Welcome to today's video. Today we are going to start with equivalent inductance. In equivalent inductance we have to consider two types of connections, namely series and parallel connection. First I am going to start with series connection. As in our previous lecture, we have already mentioned aiding and opposing connections. So I think you all are well aware about the concept of aiding and opposing connections. So first I am going to start with aiding connection. Okay. For that I am considering two coils L1 and L2 such that they are connected in series. Which is excited by a current I of t. And here I am considering a mutual inductance M such that which is aiding in nature. Mutual flux is aiding means I am considering dot on entering side of both the coils 1 and 2. Okay, you can see like this. And the voltage across this coil be V. Okay. And since this is a series connection, voltage divides and current is same which is passing through both the coils. So I can say here, let the voltage be V1 and here the voltage be V2, and we know that V equal to V1 plus V2. As per our previous lecture, the EMF, the voltage induced is nothing but the rate of change of flux linkage in a coil. That is, we can say L1 into di by dt. Okay, the current I is passing through this coil. Okay, L1 into di by dt plus there is also an EMF which is induced due to the mutual flux. Okay, that is nothing but M into di by dt. Here I consider same current I because I is passing through this L2 also. Okay, and this is nothing but V1. Okay, this is nothing but V1. And what is V2? V2 is equal to L2 into di by dt plus M into di by dt, current passing through the other coil. Here the other coil is nothing but L1, but the current is same. So I am here also I am considering di alone. Okay, then we can take di by dt as common. So L1 plus M plus L2 plus M into di by dt, which is nothing but L1 plus L2 plus 2M into di by dt, which implies V equal to L equivalent into di by dt. Comparing these two equations, we get L equivalent as L1 plus L2 plus 2M for aiding connection. Equivalent inductance L equivalent is nothing but L1 plus L2 plus 2M for aiding connection. Okay. So for opposing connection, the only difference is that here we remove the dot on this side and we'll put on the leaving side of one coil and the entering side of the other coil. Okay, we can make some changes for opposing connection. That is, in series connection, first part is aiding and the second is nothing but opposing connection. Here I am making some changes in it. Okay, that is enough for deriving the equivalent for opposing connection I of t. and I am replacing the dot on leaving side of this coil. Okay, and the difference is nothing but here plus is replaced by minus, here the plus is replaced by minus. So L1 minus M plus L2 minus M, L1 plus L2 minus 2M into di by dt v equal to L equal to di by dt, which is nothing but L1 plus L2 minus 2M for opposing connection, for opposing connection. So we need to remember these two formulas for aiding and opposing connection. Next is we have to find the equivalent inductance for parallel connection. Equivalent inductance for parallel connection. In parallel connection, current divides and voltage will be same. Current divides and voltage will be same. Let's go through the example. Parallel connection. Parallel connection. In parallel connection, aiding. In parallel connection, first case is aiding. Consider two coils L1 and L2 which are connected in parallel, as I will consider a current I of t and which is divided as I1 of t and I2 of t. Okay, and this is nothing but L1, L2, and let V be the voltage across this coil and V1 be the voltage across this coil and V2 be the voltage across this coil. And from KCL we know that I of t equal to I1 of t plus I2 of t, and also from this equation it is clear that V is equal to V1 equal to V2, V is equal to V1 is equal to V2. Since a current is passing through this coil N1, there will be a voltage induced V1 which is given by L1 into dI1 by dt, dI1 of t by dt. Since self-induced EMF is contributed by the current which is passing through the same coil, and there is also a mutual inductance M associated between these two coils, as there is a coupling between these two coils M, and since it is aiding in nature, we consider the dot on both the coils of entering side. Okay, so due to this second coil, the mutual induced EMF is nothing but M into current passing through the, due to the current passing through the other coil, that is dI2 of t by dt. Okay, and V2, in the same way, V2 is nothing but L2 into dI2 of t by dt plus M into current passing through the other coil, which is nothing but dI1 of t by dt. Okay, and for simplicity I am taking the Laplace transform of both these coils, Laplace transform of both this coil, that is V1 is equal to for differential terms while taking Laplace transform we consider S into L1 into I1 of S, V1 of S equal to V1 of S is equal to S into L1 into I1 of M into S into M into I2 of S. What is V2 of S? V2 of S is equal to S into L2 into I2 of S plus S into M into I1 of S. Okay, and From equation, let this be equation 1 and this be equation number 2. From equation number 2, we can equate these two. Let this be equation number 3 and this be equation number 4. From 2, we know that equation 3 equal to equation 4, that is S into L1 into I1 of S plus S into M into I2 of S is equal to S into L2 into I2 of S plus S into M into I1 of S, and taking the common terms, let I1 of S equal to S into I1 of S is equal to L1 minus M. S into I2 of S is equal to S into I2 of S L2 minus M, and we will cancel common term as from this equation. From this equation we get I1 of S is equal to I2 of S into L2 minus M divided by L1 minus M. Okay, let this be equation number 5. And taking Laplace transform of this equation, I of S is equal to I1 of S plus I2 of S. And we can derive I1 of S and I2 of S in terms of I of S. Substitute equation number 5 in equation number 1. We can change this as equation number 1. Substitute 5 in 1. Substitute 5 in 1 so that I of S is equal to I2 of S into common. We are taking I2 of S as common, L2 minus M by L1 minus M into, plus 1, which is equal to I2 of S into L1 plus L2 minus 2M divided by L1 minus M, I of S, okay, which implies I2 of S is equal to I of S into L1 minus M divided by L1 plus L2 minus 2M. This is equation number 6. Equation number 6. The same way we can derive an equation for I1 of S. I1 of S is equal to, from this equation we can write as I of S minus I2 of S. That is, we can take, substitute 6, equation number 6 here. I am taking I of S as common. I of S 1 minus L1 minus M by L1 plus L2 minus 2M. Okay, that is I of S into L1 plus L2 minus 2M minus L1 plus M by L1 plus L2 minus 2M. that is I1 of S is equal to, cancel these two terms, L2 minus M divided by L1 plus L2 minus 2M into I of S into I of S. So we get two equations, I2 of S and I1 of S in terms of I of S. Let this be equation number 7. Next, we have to substitute equation number 6 and 7 in equation number 3 or 4. I am considering equation number 3 now. So when we substitute equation 6 and 7 in equation number 3, here I have already told V1 of S is equal to V2 of S is equal to V of S. I am replacing V1 of S as V of S. V of S is equal to S into L1 into I1 of S. I1 of S is what? I of S into L2 minus M divided by L1 plus L2 minus 2M plus S into M into I2 of S. I2 of S is nothing but I of S into L1 minus M by L1 plus L2 minus 2M. Here I am taking the common terms outside, that is V of S is equal to S into I of S into L1 L2 minus L1M plus M into L1 minus M square by L1 plus L2 minus 2M. Okay. Okay, and these two terms get cancelled. So the end result is V of S is equal to S into I of S into L1 L2 minus M square by L1 plus L2 minus 2M. Okay, that is V of S divided by I of S, which is equal to impedance ZL, which is nothing but S into L equivalent, which is nothing but S into L1 L2 minus M square by L1 plus L2 minus 2M, which means what? Equivalent inductance is equal to L1 L2 minus M square, L1 L2 minus M square divided by L1 plus L2 minus 2M. Okay, which is nothing but, which implies L equivalent is equal to L1 plus L2, L1 L2 minus M square by L1 plus L2 minus 2M for aiding connection. Okay, actually we no need to derive this formula, but for your better understanding I have derived for you. But you have to take care one thing is that in series connection for aiding we get L1 plus. In series connection we get L equivalent as L1 plus L2 plus 2M for aiding connection. But here in this case, for parallel connection, the denominator part is minus 2M for aiding connection, and for opposing connection, L equivalent is equal to L1 L2 minus M square by L1 plus L2 plus 2M for opposing connection. Opposing connection. Just remember like the opposite of series connection. Denominator time along. Numerator is same for both aiding and opposing connection. Okay. So just remember these two formulas. No need to derive all those things. For your sake of simplicity, I have derived all those things. So I think this part is clear to you. If you have any doubt, just comment. Okay, I will answer to you. Okay, so today the end of the section. Thank you.